I'm Anan, and today we are going to talk about quantization with guaranteed floating point neural network classifications. So neural networks are very powerful, but they require high computational complexity, significant power consumption, and large memory allocations. And because of that, it's hard to deploy them on resource-constrained devices, for example, mobile phones, smartwatches, or real-time applications. So a popular way to reduce the computational complexity of neural networks is to use quantization. And in quantization, we reduce the precision of weights and activations from floating point to a lower bit format. For example, int4, int8. Now, two approaches to apply quantization is PTQ, post-training quantization, and QAT, quantization-aware training. In PTQ, we have a training set. We train the network. After the training, we do the quantization. In QAT, we consider the quantization error in the training itself. So the resulted quantized network is more robust to quantization error. Now, both approaches are successful, but they do not guarantee floating point consistency. Means the quantized network is not guaranteed to act like the floating point network. And this brings us to our goal. We want to design an approach to guarantee classification consistency between a quantized network and its floating point counterpart. Now, to understand this, let's consider these two classifiers. We have floating point here and 4-bit, its counterpart 4-bit quantized classifier there. We feed two inputs, the blue and the green ones. At the output of the floating point, we have classification to C1. At the output of the quantized network, we see that the blue changed classification to C0, and the green stays at C1. Now, we call the blue input inconsistent because it changed classification, and the green, we call it consistent because it remains the same. Now, if we want to guarantee that the quantized network always classify like the floating point network, we need to find all the blue dots, capture them, and fix them. So the question now, can we identify all classification inconsistencies? And our goal is to detect all the inputs that now classifies differently between the floating point and the quantized network. And here we show two impractical approaches. First, you can say that we can go for all the inputs, do the tests, push them into the two networks, and store the results in some big database. Now, this approach is impractical because in neural networks, the input domain is huge, it's continuous, so we cannot do that. The second approach, also impractical, is to do that in real time. Each time we have an input, we push them into the classifier floating point and the quantized, and check the output if they classify similarly. Now, this is also impractical because if we can do that in real time, then we do not need the quantized network. We can run only the floating point network. So what requirements we want from our approach? First, we wanted to work at inference time only on the quantized network. It's important. Second, we wanted to provide a guarantee for any input to certify it as consistent and or flag it as inconsistent. And this brings us to our main idea, the QIF bound. Now, to understand this bound, let's consider again two classifiers, floating point and quantized, accepts a 2D input and classify into C0 and C1. Now, if we look at the classification results, we can see that for most of the cases, for most of the inputs, they classify similarly, they're consistent. But around the decision boundaries, in this red region, we have all the differently classified inputs. So our goal now to define a bound starting from the decision boundaries of the quantized network, expand until it covers all the red region. That's our goal. Okay, so we said that we want to capture distance from the decision boundaries, and how we do that? We depend on a common term which is called classification confidence. Now, in classification, we typically have an input. We show it to the classifier, and at the output, we have classification scores. Now, classification confidence is defined as the maximal score of class C minus the score of class C minus the maximal score of the rest labels, rest classes. And to visualize this, let's consider this figure. At axis Z, I show the classification confidence. At axis X and Y, we show the input domain. Now, we can see that at the decision boundaries, the classification confidence is 0 because we do not classify there. And it expands, it goes higher when we go away from the decision boundaries. And this also happens in the quantized network. Now, as I said, our goal is to define a bound starting from the decision boundary of the a quantized network means start from classification confidence 0 and expand until we cover all the differently classified inputs. Okay, so let's see how now we define our property using the classification confidence. We say that the quiff bound is the maximal classification confidence such that the quantized network classified to C and the floating point network classify otherwise. This means we want to find the input with the maximal confidence such that it classifies differently. If we find that, we can bound all the differently classified inputs. Okay, after we found this bound, at inference time, each time we have an input, we can compute, run it into the quantized network, compute its classification confidence, and compare to D. If it's larger than D, then it's in the gray region. If it's smaller than D, then it's in the red region. Okay, so we said how we showed how we define our property, and now let's see how we compute it. To compute it, we use MILP, mixed integer linear programming, and we have two constraints: the classification confidence of the quantized network and the classification confidence of the floating point network. Now, to encode the floating point network, we need to assign one Boolean per neuron in the network because we have one nonlinearity at the 0. But to encode a neuron in the quantized network, we need to assign b plus 2 Booleans, which is a huge number. Especially that the MILP complexity is exponential in the number of Boolean variables in our property. And how we deal with that? We use linear relaxations. We try to reduce the number of Booleans using linear relaxations, and we have here three ideas. For example, clipped parallelogram, and trapezoid. Here we just replace the nonlinearities using linear relaxations. Another idea is to use relations. Remember that we have two networks, the quantized network and the floating point network. We can add linear constraints to tie and encode relations between the optimization parameters of the two networks. We just compute the differences, propagate these differences, and turn them into linear constraints. After that, we encode that into the solver. So the solver can use this data to converge to an optimal solution quickly. Okay, so now let's describe our system. We call our system CoMPAQt. It runs in two stages. First stage, we run it once offline to compute the bound, and the second stage is inference. When we have the bound, we can run now in real time and check consistency. So our approach our system accepts as an input floating point, a quantized network, and class C. We first MILP encoding, then add the linear relaxation, then add the relations, and then push all the encoding to the MILP solver. At the output, we have our bound. From that, each time we have an input, we can run it into the quantized network, compare its classification confidence to the bound, and apply a correction mechanism if we need to do the correction mechanism. The correction mechanism is only applied if we are in the red region, what I showed previously. Okay, so now let's describe one of our correction mechanisms. In our paper, we provide two correction mechanisms, APR, adaptive precision refinement, and the quiff ensemble. And here I will explain the APR. In APR, we assume that we have a floating point and several quantized networks, for example, int4, int8, int16. Each time we have an input, we push it into the quantized network with the lowest precision. If we manage to guarantee consistency, then we finished. Otherwise, we pick higher precision. If all the quantized network failed, we fall back to the floating point network. Thus, the APR is guaranteed to always reproduce a floating point decision. Okay, so now let's talk about our evaluation setup. We evaluate CoMPAQt on several data sets, on fully connected and convolutional networks. We use PTQ and QAT as baselines, and we use matrix multiplication cost and effective bit precision as evaluation matrices. Now, to understand this evaluation matrices, let's consider this example. We have here two quantized networks, int8 and int16. The multiplication cost of int8 is 8 by 8, and the precision is 8, of course. The multiplication cost of int16 is 16 by 16, and the precision bit is the bit precision is 16. Now assume that we want to run now APR. Say we first run the int8 network, and failed. After that, we continue to the N16 N16 network and managed. Now the total cost is 8 by 8 plus 16 by 16, and the effective bit precision is the square root of this multiplication total cost. Now in this example, we can see that we produce a floating point classification result, and while we reduce the multiplication complexity compared to floating point by approximately 2x, which is the real strength of our approach. We can create floating point classification without running floating point. Okay, so here we show the APR performance. We can see that it obtains 100% consistency with floating point and reduced its computational complexity by 3.8. The baselines cannot guarantee a perfect consistency, but they have lower costs compared to CoMPAQt, which can get to 1.4 times. And here we show a case study over a system of airplane collision avoidance. We run a ACAS-Xu simulation. In this simulation, we have two airplanes, O and I. O have a neural network in it to try navigation. And all the idea is to navigate to avoid collision with airplane I. Now we run this over 10,000 simulation, and we can see that CoMPAQt reduces the floating point computational complexity by 6.25 times with average bit precision of 9.76. The path differences, if we measure the path differences of CoMPAQt and compare it to floating point network, we can see that we have 0 feet difference. And if we look at other networks, for example, other quantized network, for example, N16, N12, N8, we can see several thousands of difference in the path. Again, we can reproduce floating point results with a significant smaller multiplication cost. Okay, so now let's summarize. We address the problem of classification inconsistencies after quantization. We introduced our new concept, the quiff bound. We propose CoMPAQt to compute the quiff bound and mitigates different classifications between floating point network and quantized network. Our system employs MILP, novel linear relaxations, and relations to reduce the complexity of our problem. We propose two correction mechanisms, APR and the quiff ensemble. And we can see that we can reproduce floating point performance by reducing the multiplication cost significantly. Okay, thank you for your attention and the questions.
My understanding is you don't change the quantization method and use the high precision network results to create the low precision network. The correction in the page 8.
Here? The correction here?
8.
8?
8.
Okay.
So sorry, I forgot. Each different input have different correction parameter, right?
No, for each input we can get one correction depending on the mechanism of the correction. For each input, either we correct it or we do not need to correct it. But in the two cases, we are guaranteed to have a floating point classification. Say you can be here in the gray region, run floating point of run quantized network of N4 and get a floating point result. You don't need to run floating point after that. You get the floating point result without running the floating point. But it's proved, it's guaranteed.
It's a great talk and a significant result. I just wonder how well it scales. Does it scale for every benchmark in the Anan comp, for
Scaling
example?
is an issue, especially when we're talking about formal verification. We can scale to small neural networks, which can get to several hundreds to several thousands of neurons. But a lot of work for scaling is waiting for us, I think.
All right, thank you.
Scale is an issue. Okay, so thank you.